Thank you very much for the invitation to come and give a lecture on this subject. I will be speaking about double geometry and alpha prime corrections, and my aim is actually not to give a review talk of the whole subject, but rather to focus on a few ideas that I think are of interest and communicate one aspect of double field theory and this general field that you may find interesting, and a subject I've been working for the last few years. So this is the organization of the talk. We will begin with some introduction. In case you haven't heard anything about this subject, this will be useful. Then we go to the subject, whose mathematical background has to do with Courant brackets and double field theory. After that, we turn to double alpha prime geometry. Well, in this subject, you have to keep giving names to things to distinguish them, and sometimes it's not all that clear, but as you will see, what we call double alpha prime geometry is some special subject within double field theory. The brackets that we're talking about here, Courant brackets, admit what are called alpha prime deformations, and they are related to the old mechanism of Green-Schwarz, actually giving some geometrical insight as to what this mechanism is. From double fields to generalized metrics, as I will review the typical construction of duality covariant formulations of gravity use what is called the generalized metric. But there's also this object called the double metric. Not the generalized metric, but the double metric, and they are related, and part of the puzzles here is how to connect these two. Finally, I'll make some observations about low energy field theory and duality constraints. So, this talk is based on the following papers. The formulation that I'm going to be speaking about was done about 2 years ago with Warren Siegel and Olaf Holm, my collaborator. We developed this formulation further last year, and there are going to be 2 more papers to appear on this subject. So today we're going to be talking about this aspect of double field theory, and the subject is very big, and throughout the day there will be several talks developing other aspects of the subject, which I won't touch here. So let's begin. Supergravity theories are based geometrically in what we call Riemannian geometry. Nevertheless, we're all aware that string theory has alpha prime corrections, derivative corrections that are typically quite complicated, but there must be a reason for them. They certainly make the supergravity stringy, and you would wonder if there's a geometry that describes all of this, because after all, these two things together form what we call classical string theory. And classical string theory must have some nice geometry. So you could ask whether there's a symmetry principle that requires alpha prime corrections. In the case of bosonic strings, alpha prime corrections are higher derivative corrections that are written in terms of the Riemann curvature and its construction, derivatives, covariant derivatives, the field strength for the antisymmetric tensor, derivatives, dilatons, derivatives, and actions that people write for these alpha prime corrections are written in generally coordinate invariant language. So whatever higher derivative corrections you write, if you write them in terms of these tensors, this would be diffeomorphic invariant, and the gauge symmetry does not put any constraint pretty much on the kind of terms that you will have. Nevertheless, there's another symmetry that is quite interesting, is this duality symmetry. And here there's really a true surprise in some sense. When you study string theory, you study about the discrete symmetry of strings compactified on a torus. The surprising fact related to this discrete symmetry is that the massless effective field theory has a continuous global symmetry of the same type. So the massless theory, the effective field theory of the massless fields, has a larger symmetry than the full string theory. This symmetry, of course, would be broken by quantum corrections, but we're talking supergravity plus alpha prime, which is classical string theory, and that much will have this ODDR symmetry. At the early times, there was a lot of discussion of this subject, with Ashok Sen being one of the first people to explain why alpha prime corrections would preserve this symmetry. So this continuous symmetry is supposed to be there, even with alpha prime corrections. So given that you have a symmetry, an extra symmetry, you would ask, how does it work with alpha prime corrections? And there seem to be two different ways in which you can do this. In the first case, you would preserve general coordinate invariance, but admit that the duality transformations have alpha prime corrections. In the second way, you would leave duality manifest and duality transformations unchanged from the form they take for the supergravity theory. They would not be alpha prime corrections to the duality transformations, but there would be alpha prime corrections to the gauge structure, to the diffeomorphism structure. Most of the work that was done before this decade dealt with this thing, and essentially it made very, very little progress. In this current incarnation, we're trying to work more in this approach, in which through double field theory, the duality invariance will be manifest. You never have to question it. But the diffeomorphism symmetry will acquire corrections. So I can say briefly what double field theory is. It's essentially a duality covariant version of the massless theory of strings. So you take the massless sector, impose what is called a strong constraint, do duality covariant field redefinitions, implement backward independence, and you obtain something called double field theory. This double field theory has, you see it, it's manifestly T-duality covariant. It has duality covariant generalized diffeomorphisms. Diffeomorphisms are altered a little bit, and exhibits duality symmetry after dimensional reduction, which is the physical constraint. So double field theory should be thought as a tool to make duality manifest. It's not more nor less than that. Just like you use superspace to make supersymmetry manifest, you can use double field theory to make duality symmetry manifest. And you can see how far you can get with that. So when you explore alpha prime, when you explore alpha prime corrections in double field theory, it's really the same thing as exploring alpha prime corrections to the low energy effective field theory. So it's not a formal problem that you're dealing with. You're really trying to figure out what are alpha prime corrections. And T-duality imposes some constraints in the alpha prime structure of the theory, and we don't know very well to what degree this constraint is powerful or not that powerful. There's some evidence that it's a very powerful constraint, however. So, as I said, DFT is a language for duality covariant alpha prime corrections, and in principle should help us do this thing. So let's begin with the first point that appears in this subject, something called Courant brackets. So Courant brackets are a very surprising structure that generalize Lie brackets, and they're relevant when you have a theory with a metric and an antisymmetric tensor field. you should have, at that level, gauge transformations that are parameterized by psi, which is a diffeomorphism parameter, and tilde psi, which is a one form. And you probably recognize here the transformation of the metric as a Lie derivative along the vector parameter. For the B field, also the same Lie derivative. And B, being a two form, has also gauge transformation with a one form gauge parameter that you recognize here. You can then ask what is the algebra of these gauge transformations. For that you must compute the commutator with two different parameters, and if it closes, which it does, should be a transformation with a different parameter. So the rule to construct the parameter for this commutator is what is called the bracket. So what is the bracket? Now, if you computed this bracket by yourself without ever having done this calculation, most likely you would end up with a line in black here. Here is the Lie bracket of the two vectors. Here are two vectors and two one forms. Here's the Lie bracket of the two vectors, which is a vector. And here's an antisymmetric combination of Lie derivatives of the one forms, which is a one form. So just the bracket of a vector plus a one form, and we just put them together. That's in the spirit of generalized geometry. This is an object in generalized geometry that will play a role for us. Now, if you have here, in the right-hand side, you have to have a vector and a one form. Now, notice the fundamental freedom that if your one form is exact, if psi tilde is d of something, since d squared is 0, it would not contribute to the gauge transformation. So even in the algebra of the Courant bracket, you cannot tell if there is an exact one form on this right-hand side, and there's a canonical way to construct an exact one form, which is contract the vector with a gauge, with a one form, that's a function, an antisymmetric function, and take the exterior derivative. And that's a natural one form to add here. And you could put any coefficient here if you wanted. And Courant put a minus 1/2, because for that minus 1/2, the algebra has an extra automorphism, which is quite interesting. We'll say a little more about that soon. There's another thing that is important in this structure. From two gauge parameters, you can construct a function, an inner product, which is given by this quantity. The Courant bracket is not a Lie bracket, so the Jacobi identity doesn't hold. On the other hand, the Jacobiator, which is the left-hand side of the Jacobi identity, the cyclic sum of the double commutator, should be a gauge parameter that doesn't produce gauge transformations, and that is indeed correct. That's the consistency of this formulation, in which the left-hand side, you can prove, is d of something, so it's an exact one form, and therefore you can relax and say there's no problem here, everything is consistent. So, as I mentioned, the choice that Courant made for this coefficient here is the unique one for which the algebra has an automorphism. The automorphism is constructed using a closed two form, B, and changes every element of the algebra by adding to the element a one form constructed by contracting the vector with a closed two form. And that turns out to be an automorphism of the algebra. That is to say, if you add this, if you transform the first input and transform the second input, what you get is a transform of the output, which is this quantity. And it only works for the Courant bracket. And this property, this automorphism, can be viewed as a duality transformation called B-shifts, and therefore it's highly connected with the issue of duality invariance. So, Courant brackets is one ingredient. For double field theory, we have the following situation. We double all coordinates of space-time. The normal coordinates xi are doubled. You have the xi tilde, and they're put together into a set of coordinates with an index that runs over 2d values, where d is the dimension of space-time. There are ordinary derivatives and derivatives with respect to the tilde coordinates. And this index is an ODD index. So we raise and lower indices, these capital indices, with the ODD metric eta, which is a constant metric. This is the metric that you use to define the ODD group. Another important ingredient is this object that you may have seen when you studied strings in toroidal backgrounds, called the generalized metric. It's a double-sized metric, 2D by 2D, as the indices reflect, and has 4 blocks that take a rather familiar form. This matrix is symmetric, and it happens to be a group element of ODD. So it is a constrained metric. It's a constrained object, and the constraint is just because you're parameterizing with a 2D by 2D matrix that is symmetric, the information about the metric and an antisymmetric tensor, which together comprise a D times D matrix. The way the constraint is expressed is by saying that if you define the raised index version by raising with etas, that object turns out to be the inverse of this object. So you can raise it with this group invariant metric and get an object. Now, if your double field theory is supposed to give you the same physics as the low energy effective actions of field theory, you should impose what is called the strong constraint on every field and every gauge parameter, and in every product of fields on any object of this theory. This should be true, this Laplacian condition. You probably shouldn't focus on that one if you never have heard about double field theory. There is a constraint. There's a possibility that someday double field theory will relax this constraint in an efficient way, and Marquez, Grania, other people have made interesting suggestions how to do that. I will not consider that in this talk, but it may be a direction in which the field moves in the future. Just like the coordinates fit nicely into a doublet, the gauge parameters fit nicely into a doublet of gauge parameters. So whenever you see a psi with an M index, you have the one form and the vector parameter together. So the gauge transformations, in gravity theory, you would use the gauge transformation, as we've seen, is a generalized Lie derivative of the metric. In here is the ordinary Lie derivative on the metric. Here it is the generalized Lie derivative on the generalized metric. The generalized Lie derivative has a few terms, like this one, the first one here, and the second one here, that are very familiar. But then it has some strange terms in which the indices seem to be in the wrong position. A derivative with an index up and a gauge parameter with an index down. And these things make sense in this theory because you have the flat metric, the eta, to raise the index or lower the index here. So this is the way this should work here. And this guarantees all kinds of important properties, in particular that a trivial gauge parameter generates no gauge transformations. The generalization, remember, if you have an exact one form, no transformation for the B field. In the double context, if you have an exact gauge parameter, you should have no transformation of the generalized metric. And that happens thanks to these extra terms. The algebra of gauge transformations gives a C bracket, first seen in the work of Warren Siegel. And this is the C bracket of two gauge parameters. Here, these parameters have these capital indices, so it's the whole algebra here of xi's plus xi tildes, because you're using now the ODD indices. And a C here for C bracket, and the name C bracket is really making you think about courant, because as it happens, this bracket has this term that you would recognize as the standard Lie bracket, and then an extra term where again you see funny things. A derivative with an index up, and a gauge parameter with an index down. You wouldn't have this in ordinary geometry, but here you do have it. And this is the gauge algebra of the double field theory. As it turns out, by the time you eliminate the doubled coordinates, by setting the tilde derivatives equal to 0, this bracket with the 1/2 reduces exactly to the courant bracket. So the 1/2 of the courant bracket really comes from this extra term in some combination. So this is double field theory, really. All we really need to know at this moment is a reformulation of the low energy effective action with two derivatives. And I have not given you the action, but the action is given by some curvature invariant of this. So I want to turn now to the doubled alpha prime geometry. So the double field theory so far has generalized diffeomorphisms, no higher derivative structure, two derivatives. It's essentially equivalent to supergravity. What is the advantage? You've reformulated it with manifest ODD symmetry. So you don't have to do what people did painfully for many years, which is do a dimensional reduction and discover an ODD symmetry. The formulation of the theory has an ODD, a formal ODD symmetry to begin with, so that you're guaranteed that after dimensional reduction, you will get the ODD symmetry. So if you're worried about T-duality, if you have the theory formulated as a double field theory, the T-duality is there. So I now move to this doubled alpha prime geometry, and this work is an approach to do a double field theory, but with alpha prime corrections. As it turns out, the work that I'm going to describe puts alpha prime corrections into the theory, extends the gauge symmetry, but it turned out to be fairly difficult to recognize what was the theory you managed to build. And essentially, we've been working on that, trying to understand what is the theory we constructed. What I will try to argue is that the theory is interesting and deserves some attention. So we took, and this is the work we did with Warren Siegel, we took his original formulation and extended it quite a bit as follows. First thing is that we use conformal field theory methods to construct the double field theory, which is a major simplification, as you will see. So how do you begin? This equation perhaps is the most surprising one of all conditions. You see, we've doubled the coordinates. Think of them as double coordinates of a single complex variable that has enough to describe the closed string theory. And this time, if you remember, when you learned string theory, xi with xj was gij times this logarithm. But here, instead of putting the metric or the generalized metric, we put this constant background independent metric. That is a pretty strange departure of this in this field, and has very surprising consequences. So you build a conformal field theory this way. In this way, the currents have this OPE, and you will consider three types of operators: scalars, vector operators, and tensor operators. The dilatant field that depends on the coordinates is an example of a weight 0 tensor. Gauge parameters have one index and are an example of a weight 1 tensor. And the double metric, you might think first the generalized metric is HMN, it's a two-index object, it's a tensor. You have this thing. And as it turns out, you can construct another thing of weight sec 2 by taking one derivative, which increases the weight, on something of weight 1, which is something like this. So you have the generalized metric and you have another object here. So, for example, if you take a derivative, a world-sheet derivative of a function, you use the chain rule, and you have this. So it's of weight 1. It has one, it's an object with one index contracted. Gauge parameters are of weight 1. Remember, they were of this form, and they coupled to a current. And you can compute gauge transformations by doing what you do in conformal field theory. You integrate the current and take the commutator with the object you want to compute its gauge transformation. So you do this. When you postulate such a thing, the algebra of the gauge parameters, the A's, must close, and whatever you define as a tensor field, B, must contain enough structures that the right-hand side, which is the variation of B, can be interpreted as truly a variation. So there's actually two kinds of symmetries: gauge symmetries generated by this kind of object and conformal symmetries. Now, using the OPE, you can define an infinite sequence of products of operators with the operator product expansion. So if you have a tensor and another tensor operator, you call this a product of weight W. Independent of the weights of A and B, this will be a product of weight W. And the OPE of two operators will take this form and will induce operators of different weights. So for example here, if you have two operators over here, the leading term in the OPE will have the sum of the weights and will be multiplied by an operator of weight 0, which is a product of weight 0 of these two operators. So for example, the product of weight 0 is an overlap, so it suggests it's a scalar operator, is weight 0. So if you define products this way, and gauge transformations the way we've defined, you will be guaranteed that the tensors, products of tensors are tensors and are covariant. So everything will multiply properly and transform properly. I want to just mention that you can derive the Courant bracket and the similar quantities by doing OPEs. So if you have two gauge parameters here, remember this size were products of gauge parameters times currents. You can do the OPE and you get a weight 0 object, a weight 1 object that must be a tensor, and that's what's called the Dorfman bracket. And if you do the OPE in the way that you express the fields as you do in conformal field theory around the second point, this is at Z1, at Z2, and you express these things at Z2, you get what are called Dorfman brackets. And if you expand in an average around the first point and the second point, creating symmetrized structures, you discover the inner product and the Courant bracket. These two brackets are related by a total derivative, and it comes from the OPE. So it's a pretty nice thing that all these brackets just arise from commutators, and the difference of the two brackets is a familiar thing that physicists know about expanding an OPE around different points. I will just not go through this because we will run out of time. So in order to construct the gauge algebra and to calculate the bracket, you simply have to do this OPE that you have in here. So the OPE is this OPE here. And you can do this OPE to get, for example, the 0 product, the overlap. When you did a contraction between the dx and the dx, you got a term with 1 over z squared and the product of these two xi's, which is the familiar term in the overlap. But when you do a contraction between dx and xi's and dx and xi's, you get this term. Mu is a higher derivative correction. It also produces a higher derivative correction of the Courant bracket, or the C bracket, better say. And here it is. This was the C bracket, the thing that gives you the Courant bracket when you truncate the coordinates, and here it's its higher derivative correction. It's a unique term that you can have in this bracket, and no other term can be written that is consistent with the structure of the theory. So this is a pretty nice thing because you've deformed the C bracket non-trivially by adding a higher derivative correction, and it's the only thing you can do. So the dynamics involves a double metric, as we will see. You could begin by thinking, oh, that's the generalized metric, but the equation of motion will not be the same as the generalized metric. So how does this operator begin with? Well, it arises from a tensor operator. You can define a tensor operator in which an object like a metric is in here. And then, as I mentioned, the tensor operator has an extra piece, and here this object is an auxiliary field to be determined. The gauge transformations of these fields are uniquely determined because you just do the OPE with the gauge current. So the gauge transformations can be derived immediately. There's no problem whatsoever. Where do you introduce the dilaton? You can introduce it from another tensor. Here is a tensor in which the metric is the eta metric that constructs the indices. And here there's an extra piece of this form, partial derivative, in fact two of them, on the dilaton. You can check that this makes sense by calculating the gauge transformation of that object and deriving that the dilaton gauge transformations are the ones you know and you like. Now these two objects will play the role of Virasoro operators. And therefore you can try to see if these Virasoro operators form the Virasoro algebra. So again, it's a computation in conformal field theory because you have all these operators. And you can try to see if this structure is produced. Now, remember we defined products, and the S field, the one that contains the dilaton, is a very special object, contains the eta metric and the dilaton. And it helps you define, if you take a product of a tensor with S, and it should be a scalar, it constructs a scalar out of the tensor, and it's what we call the trace. It begins with an ordinary trace, and then it has higher derivative corrections. If you want to construct an object of weight 1, that's the divergence of the tensor. It begins as the divergence and has higher derivative terms. And thus, for example, the OPE of S and T must have a scalar that appears with these are weight 2, so weight 4 times the scalar, the zero product, and a weight 3 with the divergence here. If you look here, you see that the z to the 4 pole and the z to the 3 pole are missing in order to have a Virasoro algebra. So you learn that the trace of this object tau and the divergence of this object tau must be 0. So indeed, if you compare with the Virasoro equations, you get that the trace is 0, the divergence is 0. From the TTOPE, you get a redundant equation and a non-trivial equation. By the time you translate it, this equation takes the form of the double metric squared being equal to 1 plus an object with 2 derivatives, 4 and 6 derivatives. So the double metric satisfies this equation, that's the equation of motion. And if you neglect the alpha prime corrections here, it would look like m squared equal 1, which is the thing that the generalized metric satisfies. But on the other hand, for a complete structure, this metric is not the same as the generalized metric. So what you see is that in order to put together this theory, you need to have an object that is not quite the generalized metric. The object that appears in the theory as a tensor is a doubled metric. It doesn't have a constraint. Remember, h squared essentially, by the time you compose the indices, is equal to 1. So that's why it's a constrained object. M is not, and that is the main thing that you must realize. So, well, we've been building this theory little by little, doing this conformal field theory stuff. You still would like to build an action for this theory as well. So we have all these structures, we have the products we define in here. How do you build an action? Well, we said that the field tau that contains the double metric is supposed to be divergenceless to begin with. So given an arbitrary tensor, we can define a projection that gives you a divergenceless tensor. And that actually plays some role. Remember, a tensor has, where we put here the double metric and an auxiliary field. To make it divergenceless, actually what happens is that you must replace the auxiliary field by some specific function, gm, that I haven't written here, which is a function of the two-index field and the dilaton. So when you put this field just depends on the two-component object and the dilaton, and it's divergenceless. You can also define a star product, which is a product in which you take two objects, make a tensor, an object with weight 2, and then take its divergence, make it divergenceless. And this product happens to be symmetric. OPEs are not necessarily symmetric. Don't lead to symmetric products. So by the time you do these operations, it happens to be symmetric. Moreover, a quantity of this form, an integral of the dilaton times the inner product of a tensor and the star product of two tensors is totally symmetric in 1, 2, and 3. And that's what you need in order to write an action that gives you the whole double field theory. This action, since this is symmetric under every possible exchange, when this is a divergenceless tensor, as it is, when you vary for tau, you can vary simply 3 terms here, and you get a factor, and you get the equation of motion that will have tau squared is equal to 2s. So this is the full double field theory, and all these things are calculated in terms of OPEs. So you have a very simple structure of this theory, a cubic theory. Now, you've seen, and every OPE in this object, in this theory, has alpha prime corrections. You've seen the alpha prime corrections show up in higher derivatives when you take OPEs. So this theory is full of alpha prime corrections, but they preserve T-duality exactly. So this theory is the focus of what I'm speaking here today, and I want to understand what it is. So what does this action describe? How is M related to conventional fields? And what is the action in terms of conventional fields? So in order to, you may have gotten lost with this discussion. So what does one want to take out from here? Well, the first thing is that this action involves a field T. And what is T? T is the double metric, and this field that is determined in terms of the double metric by the divergenceless condition. So T is a conformal operator here. What is S? Is a field that has the dilaton, a conformal operator. What is the action? An overlap here, which is a zero product. Another product, so basically OPEs, and an overlap. So this can be constructed, and if you had truly a couple of hours, you could write the theory in terms of M with all the higher derivatives that it has. It will have up to 6 derivatives. And the natural conjecture which we made at that time and was erroneous is that this is the alpha prime corrections of the bosonic string theory. And it turned out to be different from that, and I want to explain that. So we now leave this theory for a second, and we're going to try to understand what it is. And the first point that will go in here is to remember that in this theory, the gauge structure of the C bracket had an extra term. So we want to understand what that is. So it's deform brackets. So remember, when you have a C bracket, everything is duality covariant. And if you want to know physically what it is, well, reduce down, just like the C bracket became the Courant bracket that mathematicians and you understand well, ask the same question. Reduce it to the physical subspace, and what do you get? Maybe this whole construction is formal, and by the time you reduce, you get just nothing. But no, it's not formal. Here is the C bracket, the deformed C bracket. We just put a prime here. This was the naive bracket. This was the Courant bracket. And here is the extra higher derivative terms that show up. So the Courant bracket will be deformed by these things. What are these? Remember, this extra term was a one form. This is also one form. All the subtleties of deforming brackets have to do with the one forms always. So what is that one form? This one form uses two vectors to construct the one form. Basically, you have this thing, the exterior derivative of vector contracted in matrix form. So it's the trace of this, and even with more indices, the dv and the v with L and the k here are contracted like a matrix. This is the trace here reflects what happens with these objects, that each one has an index, and there's a di here. So this is, you see, two derivatives, three derivatives. Remember, in the brackets, these have one derivative, so this is a term with three derivatives. It's an alpha prime correction. Associated with this bracket, there's also a deformed inner product that we obtained in this double field theory. And here is an extra function associated to two vectors, and the function is the trace of this thing. So there's the one form for the C bracket, the vector here. So this is apparently a unique deformation of the Courant bracket. Certainly this didn't seem to be known by mathematicians, but to physicists it is related to a nice story, as we will see now. Now, you would say Courant brackets are based on ordinary geometry. You're adding a derivative, you're ruining the geometry probably, but you see, you're getting a consistent bracket, so it's just a deformed geometry with deformed Lie derivatives. The full Lie derivatives now are the generalized Lie derivatives plus something with the higher derivative terms. On scalars, the new derivatives are the same as the old ones, and gauge transformations must be defined with Lie derivatives. And finally, the objects we have, the deformed brackets and the deformed inner products, are consistent, are gauge covariant objects. That is, This transforms as a scalar, and this transforms as a vector under gauge transformations. So it's unusual, but all is well with it. So you could ask, what are the gauge transformations that generate the deformed bracket? So remember that these transformations that we have here generated the Courant bracket. So you could ask, what, now that you have a deformed version of the Courant bracket, what extra term should be in here? And this is the higher derivative term that you must put. You must put something that transforms a 2 form, so this thing must be a 2 form. How is it built? Well, this object is a matrix-valued function, and the Christoffel connection can be thought as a 1 form with two matrix indices. So the trace contracts the 4 indices as matrices. Here you have a 1 form, and this D forms another 1 form here. So if you prefer to see explicit indices, here it is. The matrix-valued 1 form of the Christoffels is this, and this term would correspond to this kind of transformation. It's a higher derivative transformation. So this is a deformation of the algebra of diffeomorphisms, and you have here what this thing is. So this theory that we've written has this deformed bracket, and this deformed bracket would come from deforming gauge transformations in this way, and you should ask, so have we seen this in physics before? And this is, in fact, the way the gauge transformation of the antisymmetric tensor field is modified in the Green-Schwarz mechanism. Indeed, in the Green-Schwarz mechanism, this is the transformation of B that you need in order to make the Chern-Simons corrected field strength for the B field. The B field, the exterior derivative, is the field strength. But in the Green-Schwarz mechanism, you add the Chern-Simons form of the, people wrote it at that time, of the spin connection. We're working in a metric formulation, so we do it of the Christoffel connection. It's really equivalent. See, this is a Chern-Simons 3 form. And you know that the Chern-Simons 3 form is not generally covariant. It has an anomalous transformation. And this anomalous transformation is cancelled by the now anomalous transformation of the B field. So you achieve a cancellation thanks to the anomalous transformations. So what you realize then is that this theory you started to build with higher derivatives and alpha prime corrections is incorporating the Green-Schwarz mechanism. It has an algebra that is consistent with modifying the B field gauge transformation in this way, and therefore it would produce a gauge invariant H field properly, just as Green and Schwarz did it. So this brings me to the last part of the talk, where we try to understand this whole thing a little better. So what do we have here? We got the theory with alpha prime corrections and with duality invariant. Nevertheless, we got a theory with a field we're not familiar with, the double metric M. Physicists are accustomed to the generalized metric H. That is a well-known object, but the double metric is not well-known. I think it's the first time it's being used. So we wrote the theory in terms of M, but nevertheless, before we did this construction based on conformal field theory, everybody was trying to write a theory with higher derivatives in terms of the generalized metric, because the nicest formulation of the double field theory, or at least the simplest, was with a generalized metric. So it was natural to use the generalized metric to do the alpha prime corrections. Nevertheless, somehow, by these conformal field theory methods, you're led to a double metric, not a generalized metric. So the question you can ask is, can you give a formulation in terms of a generalized metric, that it would be more familiar? So this is discussed in a couple of papers that will appear, I think, this week, and done with my friend Olaf Holm. And let me tell you a little of what's going on. The generalized metric encodes the metric and the B field. The double metric is as big as the generalized metric, but is not constrained, so it has more degrees of freedom. Those degrees of freedom must be auxiliary. So the double metric encodes the metric, the B field, and lots of auxiliary fields. Somehow, presumably very important to simplify the theory. So given a generalized metric, if you had a generalized metric, I told you that it's basically squares to 1. More precisely, these things are true. It's a constrained object. And therefore, there are two kinds of projectors. A projector into one kind of indices and a projector into another kind of indices. When you vary a generalized metric, you must preserve this constraint, and that implies that the variation of a generalized metric being a constrained object, the generalized metric is a constrained variation. And the variation of the generalized metric is such that it involves the off-diagonal projections, different projections on the left and on the right. Of course, if you add it here plus P transpose plus P bar transpose, that would be just an identity, because you can put projectors on the left and on the right. So think of the double metric and attempt to write it as a generalized metric, which would be the case if alpha prime was 0, plus corrections. Since little fluctuations of H include the off-diagonal projections, it's natural to constrain F to just include the diagonal projections. Because if this is perturbative and would have off-diagonal pieces, they could be absorbed into H. So this seems a natural way to try to expand a double metric in terms of H plus a constrained object where the projectors depend on H. So in our earlier work with Siegel, we didn't know how to do a systematic expansion of the double metric in terms of generalized metric, but this seems to succeed. You can then show from the equations of motion that F turns out to be an auxiliary field, so the auxiliary part of M is actually in F. The equations of motion of M allow for an algebraic solution of F in terms of H, the dilaton, and derivatives. So if you're willing to work, you can solve for F recursively and find an expression for F in terms of H and derivatives, and then M can be plugged back into the action and you got the theory. This gives you a systematic procedure to write the double field theory written in terms of the double metric as a fully non-polynomial double field theory of a generalized metric with all numbers of derivatives. So we see what seemed to have been some of the difficulty in this field is that while the theory in terms of the double metric, I show you the Lagrangian, was cubic, if you attempted to write higher derivative corrections in terms of the generalized metric, it would turn out to be fully non-polynomial. You would never be able to stop. So the cubic double field theory in terms of the double metric includes all orders of alpha prime if you write them in terms of the generalized metric. And we would imagine, unless there's a miracle, it would include all orders in alpha prime when you write it at the end of the day in terms of G and B. So a theory that is cubic in terms of the double metric and has alpha prime corrections to order alpha prime cube only generates, by the time you go to more conventional variables like generalized metrics or metrics, it generates all orders in derivatives, apparently. Now, if you're curious how the transformation of the generalized metric changes, remember you had a Lie derivative to begin with. The first order correction looks like this, terms with 3 derivatives. Here's one derivative. There's another derivative and a k, which is like an anti-symmetrized version of the derivative. So this is the expression, and if you had attempted to construct this double field theory in terms of the generalized metric, you probably would never be able to do it. Would be very, very difficult. So, how does this theory really look? So, if you do a perturbative analysis of the double field theory with the M field, you realize after some work that the action that I wrote here is a correct representation of the theory to order alpha prime. Let me go slowly over this. Here is the familiar action. This is the normal action for the massless degrees of freedom of a string. And if this would be the normal H field, that would be it. Now, we're talking about a theory with a Green-Schwarz mechanism. So H is the H field plus the Chern-Simons 3 form that comes with an alpha prime. So this object is gauge invariant. And this is what you need for a kinetic term. So this theory, as I've written it, has order alpha prime corrections coming from expanding this product and taking the first order in alpha prime. But it also contains alpha prime corrections squared, in which you have the square of this term. Now, so look at this theory. It has alpha prime corrections and alpha prime squared corrections. It is exactly gauge invariant, perfectly gauge invariant, because with the modification of the B field transformation and this thing, H is exactly gauge invariant. So this is a theory that is exactly gauge invariant and has order alpha prime corrections and alpha prime squared corrections. But the question is whether it's T-duality invariant. You see, we don't know. We know how to write this double field theory in terms of M. We now know how to write it as an infinite sequence with the generalized metric, and we've never written it in terms of G and B. So how will it look in your familiar variables G and B? Well, this perturbative analysis shows that working with the double field theory, you can prove that to order alpha prime, this is correct. Now, you might be tempted to say, look, you got an infinite non-polynomial version with generalized metrics, but maybe there are field redefinitions, and actually by the time you write it in terms of G and B, this is the action. All this thing you wrote is just this. For that, I would need to know if this theory with order alpha prime square terms is exactly duality invariant. Because the main thing that you've achieved is alpha prime corrections with exact duality invariance. So since S, as I said, is exactly gauge invariant, we can ask, is this action S exactly duality invariant? If it would be exactly duality invariant, there would be some evidence that this whole double field theory is just this, and would be very surprising that something like this is exactly duality invariant. Well, we were faced with a problem of testing duality invariance to order alpha prime squared, which is very difficult in principle. There's a procedure that Meissner invented many years ago to test T-duality by reducing to one dimension. This suggestion by Meissner and this procedure needed a little development to implement field redefinition freedom, which can confuse all your calculations unless you deal with that properly. So we've developed that, and we're going to show how it's done. And with this method, you can test the duality invariant of an action. In particular, you can easily see if a theory is not duality invariant. So as expected, the order alpha prime action that we wrote is consistent with T-duality. But the order alpha prime squared action, which would be if you kept everything here and said, okay, that's the whole act, that definitely is not duality invariant. So this theory must have a lot more terms, and most likely it's infinitely non-polynomial in alpha prime. So the order alpha prime action is not consistent with T-duality, and this cannot be the whole story. So let me conclude. It's been a long talk. And summarize and make a few observations. So first, an apology. I've explored only one angle of double field theory, trying to use it to understand alpha prime corrections in string theory. A very interesting problem, but not all you can do in string theory with double field theory. So there are many other applications of double field theory. They deal with non-geometric compactifications, flux vacua, as well as attempts together with generalized geometry. And there's a nice interplay between double field theory and generalized geometry to give a new and more suitable formulation of some limits of string theories. So there's a lot of work in those directions. Some of it you will hear today, and it's fairly independent of what I talk today here, but it's very much in flux. So even within the scope of alpha prime corrections, I have not attempted to explain all possible approaches in the literature. And there's work by Marquez and Nunez, quite interesting recently, the Godasgar brothers, Coimbra et al., a little more in the setting of generalized geometry. And there's a general push at this stage to see what T-duality does for alpha prime corrections. So I did focus on the formulation of alpha prime deformed DFT with a double metric, even though, as I probably emphasized by now, it doesn't correspond to some specific string theory. We initially thought it would be the bosonic string, but it's the bosonic string to two derivatives plus the Green-Schwarz mechanism. And it doesn't have the gauge fields of the heterotic string. So it's neither the bosonic string nor the heterotic string. So it does not correspond to some specific string theory, but I did do this because it's an example of things we wish to understand and achieve more generally. So what does it exemplify? Well, the theory we wrote is simplified dramatically by the use of a double metric. So it achieves something with a double metric that you could not achieve apparently with a generalized metric or G, V, and phi. It's a cubic theory that describes gravity with all number of alpha prime corrections. With a generalized metric, it would be non-polynomial. So it certainly allows you to do something you would not achieve with a generalized metric. In the M formulation of the theory, you have terms with up to 6 derivatives. In H, G, and B, 5 variables, it has derivatives to all orders. What would be its claim to be doing It's a duality invariant completion of the Green-Schwarz mechanism. Basically, it takes the Green-Schwarz higher derivative corrections and adds all that it's needed to make it exactly duality invariant. So this theory is not the bosonic string nor the heterotic string, but it's a duality invariant, exactly duality invariant theory with higher derivative corrections, where the first derivative corrections are the ones of the Green-Schwarz mechanism. And then you add all that is needed to make it duality invariant. I suspect is the simplest gravitational theory with derivative corrections that is exactly duality invariant. In fact, it seems much harder to do the bosonic string with Riemann squared terms than to do this theory. This theory is almost a little topological due to the geometry of the Green-Schwarz mechanism. So it's perhaps the simplest gravity theory with derivative corrections. You see, as soon as you turn on a derivative correction, apparently duality invariance will force you to add infinite number of derivative corrections. And that's a very complicated procedure, but this theory in m variables does it all in one fell swoop. So it also has a symmetry principle for alpha prime corrections. So you can understand from the point of gauge invariance what this theory is. And it's pretty nice also as that theory. You have the Courant bracket. Well, it implements as a gauge symmetry the unique higher derivative deformation of the Courant bracket. Was one term. You cannot write terms with order alpha prime squared in the bracket. There's just no way you can do it. So it's a unique extension of the bracket, and that's the theory that it's built from that. For all these reasons, I think this theory really, we would make great progress if we would understand it really how it works, and it would help us do things as efficiently for the other alpha prime corrections. You know, people have never been able to write the full form of alpha prime corrections to all orders in theories, and this is not quite a string theory, but it has all the alpha prime corrections that you need for duality invariance. So we should understand alpha prime deform double field theory, and I think it would be nice to understand in general how higher derivative corrections can be made consistent with exactly duality. For this alpha prime deformed double field theory, the m variables are extremely efficient, and it's an open question whether in terms of a metric, a B field, and a dilaton, you may find a closed form expression. Maybe there is some way with iterated connections or some iterative equations to describe the theory in terms of G and B and phi to all orders. It may exist, but it may not exist either. I think we just don't know. In a sense, what we're saying here is that we should probably understand duality symmetry in its own right. So when you have a low energy effective field theory and it has alpha prime corrections, you can ask whether it has a duality symmetry. And that's independent of string theory. And in fact, if you can understand duality symmetry in its own right, then you will understand better what duality symmetry has to do with string theory, because you would be able to determine to what degree the derivative corrections of string theory are constrained by T-duality. So, for example, the case of the bosonic string is quite interesting. If you consider the bosonic string the massless theory with two derivatives, and you ask how many terms you can write with four derivatives, well, up to field redefinitions, Seitlin and Metsaev found long ago that there are 8 four-derivative terms that can be added to the action. So 8 terms with 4 derivatives you can add to the bosonic string low-energy effective action. The particular linear combination that string theory uses 4 of these terms in some particular combination, and in fact appears to be the only possibility allowed by T-duality. So T-duality apparently fixes completely the first order alpha prime corrections of the bosonic string. Whether it does that for alpha prime squared, most likely not, but maybe yes, or maybe at some point there's a counting that says at alpha prime squared there are 2 invariants, at alpha prime cubed there are 3, and we should really learn that. So with that, I conclude my talk. Thank you very much.